Welcome to this lecture on parasite-host coevolution. Imagine a world where standing still means falling behind. In nature, survival is rarely a passive state. It is an active, relentless struggle. Today, we are going to explore one of the most dynamic and thrilling processes in biology, where parasites and their hosts are locked in a continuous, high-stakes arms race. We will uncover the biological concepts driving this battle, the mathematical models we use to predict it, and why understanding this dance is absolutely critical for the future of human medicine and global agriculture. Let us dive in. To understand this topic, let us first imagine a never-ending game of hide-and-seek between a clever thief and a dedicated security guard. Every time the security guard upgrades the locks on a building, the thief figures out a new way to pick those locks. In response, the guard installs an electronic keypad, forcing the thief to learn computer hacking. This constant back-and-forth escalation is exactly what happens in nature between parasites and their hosts. The host is always trying to develop new genetic defenses to survive, while the parasite is constantly adapting to overcome those exact defenses so it can feed and reproduce. Now that we have a conceptual picture, let us define this scientifically. Parasite-host coevolution is the reciprocal evolutionary change between two interacting species, driven by natural selection. When a host population evolves a genetic resistance to a parasite, it does not end the battle. Instead, it creates a massive selective pressure on the parasite population. Most parasites might die, but those few that happen to possess a random mutation allowing them to bypass this new resistance will survive. They then multiply, passing that successful trait to their offspring, forcing the host to evolve once again. This brings us to a famous concept in evolutionary biology. This ongoing cycle of adaptation and counter-adaptation is known as the Red Queen hypothesis. The name is actually borrowed from Lewis Carroll's book, Through the Looking Glass. In the story, the Red Queen tells Alice that it takes all the running you can do just to keep in the same place. In the biological world, this means a species cannot simply stop evolving once it reaches a certain level of fitness. Because its enemies are also evolving, a species must constantly change and adapt just to survive and avoid extinction. Before we look at the math, we must understand why this matters to us today. Understanding this coevolutionary dance is absolutely critical for modern medicine, agriculture, and epidemiology. When we use antibiotics or antiparasitic drugs, we are essentially acting as an artificial defense mechanism for the host. But just like in nature, the parasites that survive these drugs will reproduce. This leads directly to drug-resistant strains that are much harder to treat. By studying coevolution, scientists can predict how parasites might mutate, allowing us to design better, longer-lasting treatments and agricultural crops that can withstand parasitic attacks. So how do we actually study this arms race? To truly understand how this works, biologists use mathematical models to track the genetic changes in both populations over time. One of the most fundamental models is the matching allele model. This model assumes that a parasite can only infect a host if their specific genetic traits match perfectly, much like a key fitting into a specific lock. By looking at a single gene with two possible variations, or alleles, we can calculate the overall probability that a parasite will successfully infect a host in a given population. This concept leads us directly to the mathematical formula for the matching allele model. The formula calculates P, which is the total probability of a successful infection occurring when a random parasite encounters a random host. The variable x sub a represents the frequency, or percentage, of hosts carrying the first defense allele, while y sub a represents the frequency of parasites carrying the matching attack allele. Similarly, x sub b and y sub b represent the frequencies for the second defense and attack alleles. Physically, if the frequency of a specific host allele increases, the parasite population will be forced to increase the frequency of its matching allele to survive. The equation simply adds the chance of an A-type match to the chance of a B-type match. Now that we have our formula, let us see this with a concrete example. Imagine a population of snails acting as hosts and flatworms as parasites. We are given that 60% of snails have type A defenses, so x sub a is 0.60, and 40% have type B. For the flatworms, 70% are type A and 30% are type B. We want to find the overall probability of infection. We substitute these given frequencies into our equation. The first part calculates the chance of a type A match, which is 0.42. The second part calculates the type B match, which is 0.12. Adding these together gives us our final answer of 0.54. This means there is a 54% chance that any random encounter results in an infection. Before we move on to the next generation, let us analyze what that 54% really means. Because this infection rate is relatively high, it puts immense pressure on the snail population. More importantly, our calculation revealed that 42% of all encounters result in a type A infection, meaning the type A snails are bearing the heaviest burden. Consequently, the snails with the rarer type B defense actually have a massive survival advantage right now. They are simply hiding better. This survival advantage will cause the snail population's genetics to shift dramatically in the next generation, setting the stage for the Red Queen to run again. So, we have established that type B hosts have an advantage. This brings us to mathematically proving the benefit of this evolutionary shift. Let us look at what happens in the very next generation. Because type A snails were infected so frequently, many died. Now, only 20% of the snail population has the type A defense, while 80% have type B. However, the parasite population has not had time to adapt yet. This represents the lag time common in coevolutionary cycles. Their frequencies remain exactly the same as before. We set up the matching allele equation again, using the updated host frequencies and the old parasite frequencies to see how the host's shift affects the parasite's success. Continuing with our derivation, we multiply the new probabilities to find the individual match rates. The mathematical reasoning here is to isolate the success rate of each parasite type under the new conditions. The chance of a type A match has plummeted to 0.14 because the type A hosts are now very rare and hard to find. Conversely, the chance of a type B match has increased to 0.24 because type B hosts are now abundant. This shift clearly demonstrates the intuition behind the math. A previously successful parasite strategy can suddenly become highly ineffective when the host population changes its genetic makeup. Finally, we conclude our proof of the evolutionary shift. Adding the two match rates together, the new total probability of infection is 0.38, or 38%. By evolving and shifting its genetic makeup, the host population successfully reduced the parasite's overall infection rate from 54% down to 38%. We have mathematically proven the benefit of the host's adaptation. However, this victory is strictly temporary in the grand scheme of nature.
Because type B hosts are now the majority, the parasites with the type B attack allele will have a massive advantage in the next generation. Their numbers will surge, continuing the endless red queen cycle. To visualize everything we have just calculated, let us look at this allele frequency oscillation graph. On the horizontal axis, we have time, measured in generations, and on the vertical axis, we have the allele frequency from 0 to 1. The blue line represents the frequency of a specific host defense allele, while the red line represents the matching parasite attack allele. Notice how the curves oscillate up and down like waves. When the blue host line goes up, the host is becoming common. Shortly after, the red parasite line follows it upwards, representing the parasite adapting to the new host majority. This slight delay between the peaks perfectly illustrates the lag time we saw in our math, visually proving the endless chase of the red queen hypothesis.
We have covered a lot of ground today, so let us summarize our key takeaways. First, parasite-host coevolution is a dynamic, never-ending biological arms race driven by natural selection. Second, this perfectly illustrates the red queen hypothesis, where both species must constantly change and adapt just to survive. Third, we learned how to use the matching allele model to mathematically predict infection probabilities and prove how genetic shifts benefit a population. Finally, remember that this reciprocal adaptation keeps both populations in a constant state of genetic flux. You now have a solid understanding of how these evolutionary cycles work, which is vital for predicting disease outbreaks and managing resistance in the real world. Great job today.